All right, so our next quantum number is the magnetic quantum number. It gets the symbol m sub L, so it's a lowercase m with a subscript of a cursive L. And so what this does is it tells us the orientation of the orbital and actually how many there are per L. So m sub L is allowed to equal from negative L to 0 up to positive L and only whole numbers, integers, if you want to say. So for example, if n is equal to 4, L can equal 0, L can equal 1, L can equal 2, and then L can equal 3, right? All the way up to n minus 1, which is 3. Then m sub L, if L is equal to 0, m sub L can only be 0. And that's what's known as our S block or our S orbital. And you can tell that there's only one of them, right? Because L can only equal, or m sub L can only equal 0. When L is equal to 1, m sub L can equal negative 1, 0, or 1. L equaling 1, that's our p orbitals. And we can tell that there's 3 numbers, negative 1, 0, and 1. So there's 3 p orbitals. And they're just 3 different p orbitals in different orientations. When L is equal to 2, that's our d orbitals. M sub L can equal negative 2, negative 1, 0, 1, or 2. And we can tell that there's 5 of them. So we have 5 d orbitals. And then finally, when L is equal to 3, that's our f orbital. M sub L can be all the way from negative 3 to positive 3. There's 7 there. Oops. Wrong color coding up here. There's 7 f orbitals per L. And so let's think about how our electrons are going to fill. So we've got energy down here, and the electrons are going to fill the orbitals from low energy to high energy. So our lowest energy orbital is going to be the 1s, followed up by that will be the 2s. And then after that will be the 2p. Note that there are 3 different 2p orbitals. Then after that's going to be the 3s. Then the 3p. There's 3 of those. And then the 3d. There's 5 of those. And that's where it gets a little bit weird. The 4s is actually going to be lower in energy than 3d. The 5 or the 4p will be above it. And you don't have to memorize this or anything. We're going to learn how to read the periodic table, which contains all of this information. Now, when our electrons fill our orbitals, these are our little houses. They get 2 electrons per orbital. So you can think about it as though they each have a roommate. However, if they're both in the exact same orbital, you might think that they're going to have the exact same quantum numbers. And so that's where we're going to introduce our last quantum number. M sub s is what's known as the spin quantum number. And so we can think of them as, well, the 2 allowed values are plus 1/2 and negative 1/2. So we can think of them as either spinning up or spinning down. That's not quite what it means, but quantum mechanics is very complex, so we won't get into it. The way that we draw our electrons in our orbitals is we draw them as half hook arrows. Sometimes you'll see them as full hook arrows, but I like to do half hook. So we'll put one of them as spin up. That corresponds to the m sub s being positive 1/2. And then the other spin down, that corresponds to the m sub s being negative 1/2. So if we think about the address of one of these electrons, your n is going to be equal to 1, your L is going to be equal to 0, your m sub L is also going to be equaling 0, and then your m sub s is either going to be positive or negative 1/2, depending on which one you're talking about. So you can see that all of the electrons are going to have different quantum numbers. And that's what's known as the Pauli exclusion principle. right? No two electrons can have the same 4 quantum numbers. In terms of our periodic table, our M sub L values also tell us a lot about the periodic table. Redraw that. That's terrible too. Third time will be the charm. Yeah, good enough. So for example, our s orbitals, that's when L is equal to 0. So M sub L can only be equal to 0. So we have 1 orbital. And remember that there's 2 electrons in there. Well, if we think about our S block, we have 1, 2 columns, right? So same thing over here. We have our p orbitals. We have 3 of them. So that counts for 6 electrons. If you count how many electrons are in the p block or how many elements are in the p block, you'll count 1, 2, 3, 4, 5, 6 rows, right? 6 columns. The d block, we have 5 orbitals for a total of 10 electrons. Remember, it's 2 per. And then if you count how many columns there are in the d block, there are 10. And then finally, we have the f block. There's 7 f orbitals. If you think about how many columns there are here, there are 14 electrons and thus 14 columns. So we can see that the quantum numbers are all related to the periodic table, and soon we'll learn how to use the periodic table to make this all very simple.